And we're ready to start, basically. So our first speaker today will be Jorge Melendez, and he'll tell us about signatures of planet formation, differentiation, and engulfment in the chemical composition of stars. So Jorge, you can start sharing your screen. Perfect. Great. All yours.
Okay, thank you. And thank you for the invitation to speak here. So I will be speaking about 6 different samples. First, an introduction about the solar system, then about signatures in stars with planets, solar twins, open clusters, binary stars, and finally white dwarf. So let's start with the solar system. We can distinguish 3 types of planets in our solar system: the gas giants, Jupiter and Saturn, the ice giants, Uranus and Neptune, and the small rocky planets that are in the inner region of our solar system. But on top of that, we can see many small objects like moons from about 1 kilometer to about 5,000 kilometers, asteroids from just a meter size to about 1,000 kilometers, also trans-Neptunian objects like Pluto, and comets, also originated from the trans-Neptunian region or farther out in the Oort cloud. So such a diversity of bodies can be seen in this diagram of radius versus mean density. We can see that the gas giants group here on the left top panel, on the left top side. Then here we have the ice giants, and down here in red we have the rocky planet. And towards the left of the diagram, we will have progressively objects with more ice. So we can have here in the lower left side of this diagram, we have rocky icy moons and also rocky ice trans-Neptunian objects like Pluto. And something in between also, like the moon Europa. We have a possible diagram over here. It's mostly rocky, so it's close to our moon and also to Io, but it has probably some ice and also maybe a liquid ocean. So the density is going to be a little bit lower than for our moon, for example. So this is a more classic diagram used in exoplanets. Is the planet radius versus the planet mass. And here we compare the solar system planets, and also we see the same type of planets here, the terrestrial rocky planets, the ice giants, and the gas giants. So we can see that there are similar planets outside our solar system. And we can see also some diversity when we look at the rocky planets. If we extrapolate these trends and plot also Mars and Mercury, we can see that Mercury is closer to a poor iron composition. So it means that Mercury has more iron than the other rocky planets in our solar system. And that iron is mainly in the nucleus of the planets. So we can see here a comparison between the Earth and Mercury, and in the inner part of the planets, in the nucleus, this part in blue, we can see that in the case of Mercury, proportionally, it has a much larger iron core than our Earth. So the planets differentiate. When you form a planet, you can form it either from undifferentiated planetesimals and then you can build a larger and differentiated body, and then the heavy elements will sink towards the center, while the lighter elements will be on the top. So at the end, you will form a body that is differentiated. It will have siderophile elements, so like iron and nickel in the nucleus, and then you will have a lighter composition in the mantle. So it will be a latophile, so rock-loving elements. You can also build a planet already with differentiated planetesimals or something in between. At the end, you will have a differentiated rocky planet. And this is in constant evolution, especially in the initial phase of the formation of planetary systems. We have, for example, the case of the moon and the Earth. Initially, probably they have similar densities, but now you can see that the density of the Earth is much larger than the density of the moon. The density of the Earth is 5.5 grams per centimeter per cubic centimeter, and the moon is only 3.3. So that reflects that the moon has a much smaller iron core relative to the Earth. And this was because the moon is supposed to be formed after a giant impact, and part of the iron of the moon, it melted, and then it incorporated into the nucleus of our Earth. And the debris from the moon, the part that was affected from the Earth, was mostly just the mantle, just the more external part. So when we have the moon, it was mostly created from mantle material of the moon, of the previous moon, the object that some people call Theia, and from the Earth mantle. So this is why the moon has so little iron core and a much bigger mantle relative to the Earth. So another important point to consider is the dust condensation temperature in the protosolar nebula. So here in this plot, we have in the vertical axis the condensation temperature of the elements versus the distance from the sun in astronomical units. So here, closer to the sun, you have the highest temperatures, so you can have the so-called refractory materials, refractory elements, like for more closer to the sun, you can have more metals like iron and nickel. You can have condensations of those metals. And a bit farther out, still in the rocky planet region, you can have the condensation of silicates that will later form part of the mantles of the rocky planets. And farther out, you can have ices, so you can form a nucleus that will be rocky and icy, and later aggregate gas to form the gas giant planets. And this will be also the case for smaller objects. So in the inner regions, you will have rocky planetesimals, and in the outer regions, you will have rocks and ice. So this reflects, for example, the composition of small objects like the asteroids that have a larger amount of rocks compared, for example, to a trans-Neptunian object that will have a larger amount of ices. So because the dust was separated from the gas, the late gas that was being accreted to form in the final stages of gas accretion by the sun was probably poor in refractory material. So, and this may imprint a signature of planet formation. So we can have these three different signatures of planet formations. The stars may be a bit refractory poor because the dust was removed, and the late activated gas in the convection zone is a bit poor in refractory material, in material that will form rocks and metals in our solar system and in other planetary systems likely. So if you accrete a planet, you will increase the amount of refractory material. And also, because of these collisions that I mentioned it earlier, then you can break out an already differentiated body in smaller pieces, that you can have pieces that are more rich in iron, and you can have pieces that are more rich in silica, so more mantle material, or a mix of both materials. And this has been observed in the case of these planetary materials by white dwarf. So there is a lot of work on the planet-star connection, especially on the metallicity giant planet connection. You can see that stars with giant planets, they preferentially have a bit more metals, like in this work by Santos et al., or also in this classic work by Fischer and Valenti. You can see that the percentage of stars with planets, with giant planets, increase for stars with higher metallicities. On the other hand, smaller planets like Neptune's, for example, they seem to occur at any metallicity, as shown initially by Sousa and also by Luangesi. You can see that while the Jupiter mass planets occur preferentially in stars with higher metallicity, the smaller Neptune planets can occur in principle at any metallicity. And we can see better this here in this plot of metallicity for different type of planets versus planets radius. So the ice and gas giants are towards the right part. You can see that they form preferentially at higher metallicity, and on the other hand, rocky and Neptune planets, they form at any metallicity. This was shown also by Wang and Fischer. They separated the samples in metal poor and metal rich, and you can form these smaller planets at any metallicity, but they suggested that maybe even the smaller planets maybe also have some sort of metallicity planet correlation, but at a much lower level than for the gas giants. So you can see here that for the gas giants, you increase a lot the frequency, and for the smaller planets, you may increase a bit also the frequency. Lithium has been also discussed a lot in the literature. Apparently, it seems that the planet hosts have seem to be depleted in lithium, but this plot was just comparing stars of similar temperatures. Actually, when we compare twins stars, so stars in the same sample, but just one star with planets, with a star without planets, with the similar stellar parameters, not just in temperature, but also similar evolutionary states, so similar surface gravity, and also similar metallicity, then you see that both distribution of stars with planets and without planets in lithium seem similar. And later today, you will hear about by Adibekian about some more signatures of rocky planets in a recent study. So let's talk now about solar twins. We have sample that is very similar to the Sun in temperature, surface gravity, and metallicity. And for this star, we can get very high precision using the differential method. You can see that the stars seem very similar among them, but with a high precision analysis, we can detect very small variations in chemical abundances. Here in this plot, I show the difference between the chemical composition of the Sun and the average of solar twins, of this sample of 11 solar twins. And you can see that the difference is not zero. And then when you plot this difference against dust condensation temperatures, you see a very nice correlation. So the Sun composition may have some relation with planets. And we argue at that time that these smaller amounts of refractory elements in the Sun means that those elements were actually used to form the rocky material in our solar system. So, and if you put this rocky material back to the Sun, you can reproduce the trend that we found that is shown with a solid line, and the data points are is 4 masses of rocky materials that are put back in the convection zone. This was shown by Chambers and others like Jana Galarza. And this composition of the Sun being poor in refractory elements, we have analyzed about 70 stars, and we found that only 6 stars seem to be more deficient in refractory elements than the Sun. We have also analyzed lithium. Initially, we found a correlation between lithium and age, so older stars seem to deplete more lithium. And with a larger sample, we see that the Sun seems to be actually lithium poor. When we compare stars just of the same age as the Sun, plus minus half gigayear, the Sun is here by this dashed line, is the lowest star in this sample. And you can see that actually it's more typical to have much higher lithium abundance for a star, for a solar twin with a solar age. Interestingly, the star with the lowest lithium abundance also seem to have lower refractory composition. So there may be some link between lithium and planets after all. Another important element relevant to planets is thorium, that is a radioactive element that will give energy for the planet interior. And we showed that thorium, this radioactive element, is more abundant in the solar twins than in the Sun. This is a very good news, because it means that hypothetical rocky planets around other stars will probably have enough energy to keep their internal activity. So let's move now to open clusters. Open cluster is an excellent example to try to see abundance anomalies due to planets, because all the stars in the open clusters are supposed to be born from the same initial composition. So in 2014, Lorenzo Spina found that one star in Gamma Velorum have a very high iron abundance. When they look at this star in more detail, they found that apparently this star is not just rich in iron, but it seems that it has some trend with condensation temperature. So also again, this may be a signature of planets, actually of rocky accretion. Also in the Pleiades, Lorenzo Spina has studied 5 solar analogs with very high resolution and high signal to noise data. And they showed that there are some trends with condensation temperatures. So these abundance anomalies that we see in the Pleiades, they may be related to planets.
You have
Now
about 5 minutes, Jorge.
Thank you. Now let's talk about white binaries. Binaries are also important to see the signatures of planets, because both components in the binary system, they are supposed to be born with the same initial composition. And white binaries in particular are important because the stars are separated enough so that we can get individual spectra without contamination for each component. And also because this separation is very large, then the companion star will not have significant influence on the planet. So in the case of system Cygni, is the ideal system to test abundance anomalies due to planets, because one of the stars has a giant planet, and for the other star, it doesn't have a planet, at least it doesn't have a giant planet. And both stars are solar twins, so we can get very, very high precision. For this system, Ivan Ramirez showed that system Cygni A has is more abundance in all chemical elements. A more precise abundance analysis by Tushimaya et al. Showed that actually there is some trend with condensation temperature. System Cygni A has more refractory elements and with a trend with condensation temperature relative to system Cygni B. And also lithium in system Cygni A seems to be more enhanced relative to the B component. And this has been detected in several binaries with planets like HO2 in this work by Ramirez, and also confirmed by Katia Biazzo and also by Johanna Teske. Also in this system by Safe et al. And confirmed by Adibekian, and also in WASP 94 by Johanna Teske, you can see that there is some trend with condensation temperature, and also in this binary system with planets. And also in binaries, also in this HAP-P4, and also in binaries without detected planet yet, like this system, where you can see that one of the components has a huge amount of refractory elements and with a trend with condensation temperature. And also the star that is enhanced in refractories is also enhanced in lithium. Very recently, also Yonjana Galarza found this binary where they found also a trend with condensation temperature, and the star that has the most refractory elements also has a huge amount of lithium. And both stars have about the same temperature. The difference in temperature is below 25 Kelvin in this system. So the more recent study with a larger sample is by Spina et al. They analyzed about 100 binary systems, and then they found that there is a planetary accretion in at least 25% of the binary components. And they also find that the stars with more refractories, with more iron, also have more lithium. Finally, let's talk about white dwarf. In white dwarf, in some white dwarf, you can see there are metal lines, and this cannot be from the white dwarf because the metals settle very quickly. So this might be some contamination. And when you analyze this in detail, you can see that the chemical composition that you find in white dwarf is very similar to the chemical composition of rocky material in our solar system. There is a very recently analysis of many of these white dwarfs to see if they can find signatures of differentiated planetesimals. And indeed, they can reproduce these this contamination in the white dwarf, but when assuming that the planetesimals that are accreted by the white dwarf are differentiated. So they have pieces that are from the inner part of an asteroid, for example, and pieces that are from the other part, or mixed materials as well. So that's it. Thanks a lot for your attention.
Thank you very much for your talk, Jorge. There are a few questions already on Slack. The first one is by Robert, and he asks, regarding the solar twin study, where you demonstrated that Sun had initial element composition compared to other solar twins, do you know if those stars have been searched for planets either with radial velocity or the transit techniques?
Yes, we have studied this sample for a few years already, and we have found a few planets, not this specific sample of 2009, but a bigger sample of about 70 solar twins. And we found in some very interesting cases that the most interesting case is a star that has a Jupiter analog. So a planet with a Jupiter mass and with about the same separation, orbital separation as Jupiter is from the Sun. And in this case, the planet host, the solar twin, has a similar chemical pattern as the Sun. So it's also deficient in refractory elements. Unfortunately, we couldn't continue this planet survey, so we couldn't confirm yet other tentative planets that we found in this sample of solar twins.
Also connected to that question, Fabio Sordo asks, can you say something more about the typical activity level of these solar twins?
Yes, the activity level, it depends on the age of the solar twins. So the solar twins that are younger. So let me show you here this plot. Okay, so the solar twins that are over here, these typically below about 1.5 gigayear or so, 2 gigayears, especially below 1 gigayear. They are the most active. Then after about 2 gigayears, the activity level is very, very low.
Okay. Kevin also has a question. Venus and Earth have similar masses and radii, and presumably the material they formed from had similar abundances of radioactive elements. Yet Earth is tectonically active, and Venus is not. Given this, how can one argue that the amount of thorium in the photosphere of a star has direct implications for the probability of plate tectonics on any terrestrial planet it might host?
Yes, yeah. We don't know yet why is this different. Maybe Venus has a thicker crust than the Earth, but we can see. So plate tectonics is not the only geological activity that we see in Venus. There is also volcanism. So we can see that Venus is a very active planet, and yes, just the radioactive elements is not enough. If of course will depend on how specifically the planet will evolve, and will also depend on the size of the planet, because if the planet is larger, so like the case of Venus and the Earth, they will keep some activities. So Venus may have still some volcanism going on. Like smaller planets like Mars, for example, they are all tectonically dead because they will cool more quickly.
Okay, we have time for one more question by Nuno Santos. He says some studies have shown that effects related with stellar activity can produce errors in the abundances that are quite significant. Can you comment on that?
Yes, there are two recent works about that. And let me go back to here. So the changes in chemical composition is only when you go to the very active star. It's apparent change, of course. It's not a real change. It seems like it's changing, but it's actually not. So we were able to detect these changes for a star that is about 500 million years. And with a very careful differential analysis in different activity phases of the stellar cycle, we could see very tiny variations at the level of only 0.01 dex, more or less. So, but when you go towards older stars, then it's very hard to see any influence on the activity. So if you are studying very young stars, I will say of the order of 10 million years, 20 million years or so. So younger than 100 million years. Then you can see very small effects due to activity. So you have to be very careful. So the younger the star, the more careful you have to be. But there are techniques that you can use. You can select lines that are less prone to the effects of stellar activity. But for the vast majority of stars that people usually analyze in this work on the star-planet connection, I will say that the stellar activity doesn't have any significant influence.
Okay, we are out of time, but there are a few other questions on Slack, so Jorge, feel free to continue the discussion there.
Okay,